Hi, it's Bruce, and welcome once again to my Rocky Mountain Lab. And today, what I'm looking at is a Hewlett-Packard 465A amplifier. It is capable of providing times 10 or times 100 gain. The gain is accurate to within 1% at a kilohertz. It's flat within a tenth of a dB from 100 hertz to 50 kilohertz, and it's within 2 dB from 5 hertz to a megahertz. So it's a nice amplifier covering a really wide range through audio and right up to AM radio. It's in nice looking condition. There are really isn't anything to complain about. It had at one time been mounted in a panel, it looks like, but little scratching on the upper edge of the plate here, but all of the lettering's in place. Its logo is there. Terminals look good. Everything is in good shape. It's a useful tool for any time that you would need, say, an amplifier for a circuit you're working on. Could be an audio circuit, really low level, and you need to amp it up and be able to present it to a different kind of an amplifier that has a speaker or whatever. It also is useful for oscilloscopes. A lot of times your scopes, when you get down into the millivolt lower ranges, you will find that the amplifiers are not all that great in those units, and being able to amplify up a signal times 10 or times 100 and do it cleanly is something that could make quite a difference in the view of whatever you're looking at on the scope. So it's a handy tool for that. Just basically think if at any time you'd run into a need for an amplifier, say from 5 hertz to a megahertz, you could consider this one. We're going to put this one through a couple of tests just to prove that it's still holding performance. And so let me set up on that and we'll get back. Okay, so I've got this thing connected up, but how? Well, I'm bringing a sweep signal in from this sweep signal generator that'll generate a signal from, in this particular range, I'm going from about 20,000 hertz up to about a megahertz. And I'm sweeping it and displaying the results on my oscilloscope. And, well, like right now, you can sort of see a block here in the middle with a little gap maybe on each side. I don't know if you can see that or not, but I'm guessing you can. And in that block, you're looking to see if the amplitude stays steady. Now I can change the sweep rate, in which case it makes it easier to see the sweep. You can see it start low and then it's going higher to where you can't see it. And it's holding that line, top and bottom. That's our amplitude. And if I turn my sweep rate down low, very low, we can watch on my frequency meter, which I've got connected in parallel with the scope. We can see where we start and stop. It's kind of quick, but it can be seen. Here you can see a sweep from about 2,000 hertz up to about 100 kilohertz, and you'll see that it's like amazingly flat, almost perfectly flat. And then it starts the low frequency again, and then it sweeps through again. And as I change the sweep rate, you'll see me lose that lock. And we'll we should be able to pick up multiple patterns of that sweep on here. Almost got it. Anyway, you can see it repeating, and it's very flat. Now if I change my sweep up to the megahertz range, we'll start to see a drop. So you see a peak, and you see a wedge where you're sort of dropping down a little bit. That's the 2 dB loss that you get up to a megacycle. But that's a very small loss, honestly, for an amplifier over a wide range. So we're sweeping from about 20,000 up to about a megacycle and then repeating. And again, if I change the sweep rate, we can find some multiple where you can see 2 or 3 of those patterns on the screen simultaneously. Here's one. So here's the low end of the sweep, and it gets faster and faster and faster and faster till it gets to the peak, and then it starts low again. It starts over. If I slow this down, sweep rate wise, to something that is much more obvious to see, you can see the sweep going up, and we can see our signal going up. We're going to hit about a megacycle and then repeat. There's meg, and it drops right back off to 20 again. Okay, so I've made the signal start at 4 centimeters up and 4 centimeters down, and then I see that the signal drops about 3/5 of the centimeter. So we're reading about 3.4 centimeters up at the low spot. So we'll use those in our calculations. Start out at 4, drop down to 3.4. Okay, so I did a few calculations here. And if I've got a 2 dB loss that I'm expecting to see, and I have my my initial voltage is 4 units, or in this case 4 centimeters up, so my peak waveform is up 4 centimeters, then I can calculate that my my final V1 should wind up about 3.177 units, approximately 3.2. We wound up at 3.4, so we're 0.2 units better than the 2 dB loss. And I can calculate that actual dB loss as well. Let's see if we can do that. Okay, so if my final voltage is 3.4 units tall on the oscilloscope, peak, and my starting voltage was 4, so I had a 0.6 loss total, be what it is. But then my V1 over V2 is 0.85, and my formula for dB loss says 20 times the log to the base 10 of V1 over V2 equals the dB. So log to the base 10 of V1 over V2, where 3.4 over 4 is negative 0.0705811. So my dB loss winds up being a negative 1.4. So we're showing about a 1.4 dB loss over the range of, I think it was 20 kilohertz to a megahertz. So we actually beat it. So okay, so we're looking at roughly a a 4 millivolt signal coming from this Fluke 5200A, and it's coming in on the 5 millivolt per division scale, which is the lowest scale I have. And what you see is a kind of a fuzzy looking waveform there, not real very distinct or anything. And that's because of the noise primarily within the amplifier or the oscilloscope. So if I take that output from that generator and I put it into the HP465, and I take the output of the 465 and I put it back into the input here. But well, wait a minute, we're going to change the scale. Okay. And we're going to put this on times 100. And now look at that. It's a nice sharp trace compared to that fuzzy mess we had. So that's the point. And I could go times 10, in which case I could reduce the gain. There we go. So there we're at 50 millivolts per centimeter. But we had a cleaner signal a moment ago, times 100. So that's one of the uses. Nice looking unit. It's functioning within its specs, far as I can tell. And it's going to make somebody a nice little bench amplifier. Happy bidding, and we'll see you again next time, huh?